Hello, in this lecture, we're going to take on further from where we left in the last lecture. So, in the last lecture, we were discussing a problem which included an integral, solving of integral, which is dx upon 1 plus x cube. So, here I will devise a new strategy in order to solve this integral. And that strategy, I would tell that I would introduce or I would incorporate a branch point while I do an analogous contour integral. So as you know, as you're aware that what we are doing while we are evaluating some improper integrals, what I'm doing is I'm just replacing this particular integration by an appropriate contour integral. Okay. Now what happens is if now here is a very bizarre kind of strategy that I'm going to set for you. So instead of and you will have to keep patience for a while to understand why I'm doing so, and you will eventually come to know, and you'll be even surprised to know that I will end up getting the answer to this particular problem by doing an integration of this type. Now you'll be confronted upon, and you'll be confronted upon to see this, and you'll say that how come? Because see, here I was not having ln x, but I have written ln z here. But I would tell you to keep patience and listen as I move all along. Okay, it's very easy to see that z equal to 0 is a logarithmic branch point here, and there are several other singularities like e to power iota pi upon 3, and then you have you have e to power iota 5 pi upon 3, and then you have e to power iota 2 pi upon 3. All of these are singularities, and these are simply simple poles. And these singularities, this singularity that is z equal to 0 is essentially a non-isolated singularity, which happens to be a logarithmic branch point. Okay, so I've already told you that whenever you have a branch point, you have to indent the contour so that you can get rid of this kind of branch point. So what I would do, I've told you in the very previous class that I'm going to make this kind of structure or this kind of contour. So what I would do, I don't know, things don't work that way. So what? Okay, so I would do this. Okay, and what I would do is I would simply try to circumvent my origin with a circle of infinitesimal small radius, so that my branch point no longer remains in the contour of integration. Okay, so what I would do, I would simply make a circle. Let's not paste the shapes. Oh, sorry. I've already done this kind of strategy previously, so I hope you are aware of this. Okay, so this is your A and this is your B, and then you have, I think this curve entire was told as C, so I have put E, and then I'll write E, then I'll write F, then I'll write G, then I'll write H, and then I'll write J. Okay, so I will evaluate this integral, which I'm saying this. So I will evaluate this integration ln z upon 1 plus z cube dz for this curve C, for this closed contour C, which is traversing anti-clockwise. And along HJ, obviously this is a closed clockwise integral. Let's see what happens. So this particular integration is equal to integration along AB, then integration along B, D, E, F, G, H, or whatever. And then you have an integral along HGH, and then integration along HJA. So let us see one by one. Also understand that here your epsilon is a very small radius, a very infinitesimal small radius, which actually is to mainly circumvent your logarithmic branch point at z equal to 0. And here you have a radius which may go as large as possible in order to find the integral 0 to infinity dx upon 1 plus x cube. So let us move along, and let's see let us see how would integral BDEFG behave as r tends to infinity. So let us do that. So BDEFG means I'm integrating from 0 to 2 pi, and I'm on the circle. So I'm on the circle, it implies ln z. Instead of z, I will write this, then r e to power iota theta d theta, and divided by 1 plus r cube e to power iota, this thing. Okay, let us take the modulus of it. Okay, let us take modulus of it. And I've previously taught that z1 plus z2 mod is greater than equal to modulus of z1 minus modulus of z2 mod. Using this kind of thing, you can write it as less than equal to r ln r. Okay, so this is r because here will be r, iota theta mod is 1, and this will be ln r e ki power iota theta. So I'm writing ln r e ki power iota theta, this entire mod divided by 1 minus of r cube. And you can clearly see that your denominator dominates in the when it comes to the power over r. So as r tends to infinity, this entire term will go to 0. Similarly, if you try to find limit epsilon tends to 0, integration over hja, that is, you will find ln iota, ln epsilon e ki power iota theta d theta, iota epsilon e ki power iota theta d theta, and then you have 1 plus iota cube e ki power iota 3 theta d theta. So eventually, as epsilon tends to 0, this integral will also go towards 0. Okay, so this integral will always also go towards 0. That you can see. See, because you can see that as epsilon tends to 0, this is 1. But as epsilon tends to 0, here it is also there. Like this is also there. So you just see, I will let you know how it would become a 0. So here it is this. Then there is a d theta, and upon something like 1 plus epsilon cube e ki power iota 3 theta. Okay, and I'm just writing in limit epsilon tends to 0, and you have this ln epsilon okay. Okay, so I'll write an epsilon here in fact. Okay, so just remember that overall this term, I mean, while I'm integrating from I think 0 to 2 pi in clockwise fashion, so I'll write clockwise here because see it along hja I'm moving clockwise. You can clearly see that this entire integration depends on theta, and I'm integrating from theta. And this epsilon, as epsilon tends to 0, this will go towards 1. I'm not bothered about it. I'm bothered about this particular part. I'm bothered about this particular part. Okay, so let us see how would this behave. So this will be actually distributed into two. So one part would be this, and another part would simply be epsilon, and then there will be, I think, this ln e ki power iota theta will give you iota theta. So this will be iota square theta, and then e ki power iota theta d theta upon 1 plus epsilon cube e ki power iota 3 theta. Clearly, as epsilon tends to 0, this part will go to 0. There is no doubt about it, because see, epsilon tends to 0, this integral, whatever integral comes from 0 to 2 pi, I'm not interested, because anything that comes out from 0 to 2 pi, whatever comes will be a constant, and when multiplied with epsilon, and epsilon tends to 0, this will give you 0. Okay, now the first integral here, you can see this first integral here, how would that behave? So there is a problem here, because now epsilon tends to 0, ln epsilon tends to 0, this is a kind of real function here, and you can see that as epsilon tends to 0, your ln goes towards minus infinity. Okay, so ln goes towards minus infinity, and it is multiplied with an epsilon which is very small. See how to, and this particular integration is going from 0 to 2 pi. Okay, 0 to pi and theta. So whatever it comes, I'm not interested there. Whatever it comes, I'm not interested here. Rather, I'm interested in finding what limit this epsilon ln epsilon will give me, because eventually whatever constant comes out here, it will be multiplied with this, and if the limit comes out to be 0, then this entire thing is 0. So how to go about it? So what I would do, so instead of writing like this way, I will do a certain manipulation. So I'll write epsilon ln epsilon upon 1 plus epsilon. Now as epsilon tends to 0, this is going towards minus infinity, this is going towards infinity. I can clearly write my L'Hospital rule. So while I do L'Hospital, so I will differentiate the numerator part. I will also differentiate the denominator part, limit epsilon tends to 0. And overall, this will give me limit minus epsilon, and epsilon tends to 0. This limit will come out as 0. So eventually I can see that as epsilon tends to 0, this is 0. And then this is 0. 0 multiplied with any constant number would give me 0. So it is fairly easy to see that integration along HJA and integration along B, D, E, F, G, vanish as epsilon tends to 0 and as r tends to infinity. This is clearly easy to see. Okay. Now let us move ahead and see as to how other integrals would behave. Okay, so integral AB and integral GH. So how would integral AB and integral GH behave? So integral AB is nothing but integral from epsilon to r. I think this will be ln x upon 1 plus x cube dx. And while I'm integrating from g to h, so I'm moving in this direction. So this is r to epsilon. Also understand that while I'm integrating along gh, my argument has increased by an amount of 2 pi. So this is ln x e to the power iota 2 pi, and then have e to the power iota 2 pi dx. And then I have in division 1 plus x cube, because e to the power iota 2 pi whole cube is e to the power iota 6 pi, that is 1. So what you will see that if I try to write limit epsilon tends to 0, r tends to infinity, this is ln x upon 1 plus x cube dx. And this integration, this is 1, forget about it. This integration would be ln x plus iota 2 pi divided by 1 plus x cube dx. Integration from infinity to 0, and you can write it as 0 to infinity and a negative. What it will give you, see, while you are doing this ln x 1 plus x cube and ln x 1 plus x cube gets cancelled, and you are the remaining term that you can see is minus iota 2 pi integration from 0 to infinity dx upon 1 plus x cube. And remember, this is an integral which we are interested in. Okay, this is an integral in which we are interested in. So this is C. This is what we were interested in. So what I would do is, I would write it on the left hand side. So this is minus iota 2 pi integration from 0 to infinity dx upon 1 plus x cube. And don't forget, this is equals to what? This is equals to integration over a closed contour ln z upon 1 plus z cube dz, where this closed contour encloses three simple poles. Where this closed contour encloses three simple poles, you can clearly see that e to the power iota pi lies here, e to the power iota 2 pi by 3 lies somewhere in the second quadrant, and e to the power iota 5 pi by 3 lies in the third quadrant. Okay, so you have to simply evaluate integral, closed integral ln z upon 1 plus z cube dz, where the three singularities are e to the power iota pi, e to the power iota 5 pi by 3, and those singularities are isolated singularities, and they're also simply you have to find the residue of one. So this is equals to 2 pi iota into sum of residues r1, r2, r3, where your r1 is the residue about, so let us do r1 is the residue about e to the power iota pi by 3. One thing that you should understand, that while I'm doing this kind of integration and this kind of branched cut, or you can say that there is an introduction of a slit, what I have done essentially is that I'm integrating in the principal branch. So I am integrating in the principal branch. While I'm integrating on the principal branch, your ln z no longer remains a multivalued function, rather it is a single valued function. So what can be done, while I'm evaluating the residue, I can simply use the formula that when you have a function fz represented as gz upon hz, and let's say you have a simple pole at z1, you can simply do in this fashion the residue, that is gz1 upon h dash z1, provided hz1 is not equal to 0, hz1 is equal to 0, and h dash z1 is not equal to 0. This particular formula we've already proven back in our previous classes. So find residue. So it will be ln e to the power iota pi upon 3, and then you have 1 upon 3 z square. So this is z1 plus 4. So this will give you iota pi upon 3, and you have 1 upon 3 e to the power minus iota 2 pi 3. Similarly, residue about iota pi, you will get iota pi, I think 1 upon 3, and then you will have e to the power minus iota, I think 2 pi. Okay, because z square is there, and r3 about e to the power iota 5 pi by 3. So this is iota 5 pi by 3 here, because e to the power iota 5 pi by 3 log of which I will simply get iota 5 pi by 3, and this is 1 upon 3, and then e to the power minus 10 iota pi upon 3. Okay, so let us do all these three things. So let us first try to find these residues and then multiply it with 2 pi iota, and I'll write it here. Okay, so I'm doing it here. Okay, don't get confused. So this is 2 pi iota. Okay, also see that this 2 pi iota gets cancelled with this 2 pi iota, and the integral which I'm interested in, let's say this is I, is nothing but it is equals to negative of some of these residues. So not even 2 pi iota. The integral which I'm interested in, which is integral 0 to infinity dx upon 1 plus x cube, is nothing but it is equals to minus of r1 plus r2 plus r3, where r1 plus r2 plus r3 are the sum of the residues which I have written here. So this will be equals to negative of, I think I should take common iota, and I can take common pi also. I can take common, I think, 1 over 3 also. So I'm left with, I think, 1 over 3 e to the power minus iota 2 pi upon 3. Then I'm left with e to the power minus iota 2 pi. And then I'm left with e to the power minus 10 pi iota upon 3. And then I think I have a 5 here also. I have a 5 also. I think 1 upon 3 goes out, and this 5 upon 3. So 5 also remains here, and 3 also remains here. Okay. Okay. I hope it is clear till now. Okay, so what I've taken iota pi upon 3 common, and negative because here it is a negative. Don't worry about it. So 1 upon 3 e to the power minus iota 2 pi upon 3. Then I have my e to the power minus iota 2 pi, and then I have 5 pi upon 3. This 1 over 3 is common, taken common out. So I don't think there is an issue till now. So this integral which I was interested in finding is equals to minus iota pi upon 3. Let us find this integration. So this is cos 2 pi by 3. Cos 2 pi by 3 is minus half. Minus iota sine 2 pi by 3. So minus minus plus, sorry, minus, because in second quadrant sine is already negative. Sine is positive and negative because of this particular term. Then this is 1. I'm not bothered about it. Then I have 5 over 3. And understand my point. What is e to the power minus 10 pi upon 3? So I'll write here cos 10 pi upon 3 minus iota sine 10 pi upon 3, because there is a negative in between here. Also, this can be written as 3 pi plus pi by 3. So 3 pi plus pi by 3 in the third quadrant. So minus cos pi by 3. And this will be plus iota sine pi by 3. Okay, so this will give you minus 1 over 2, and then minus iota. This is plus root over 3 pi 2. So after all these things, I will write minus iota pi upon 3. You have minus 1 over 2 here. Okay, so there is a 3 here also. So this will be 6, and this will be again 6. Okay, sorry. This will be this I've forgotten. So minus 1 over 6, and then 1 is 5 pi by 6, and this 5 pi by 6 gets cancelled. So I'm not interested in this. Now I'm left with minus iota root 3 upon 6 plus 5 iota root 3 over 6. Okay, so after all, this is like 4 iota root 3 over 6 into iota pi upon 3. This will give you 2 by 3. And if this is 2 by 3, this is root 3. Minus remains there. Iota square is minus 1, so this gets absorbed. So I will become 2 pi upon 3 root 3. Indeed, this was the integral value that you also evaluated by using a very special contour, which was subtending an angle 2 pi by 3 at the center. So instead of doing this sort of integration, instead of remembering this kind of special contour, what special strategy I devised or was devised by the mathematician was to include a logarithm inside this contour of integration. And eventually I found that this harmless term, inclusion of this harmless term, does not impact much of our integrals, because see, eventually this integral has become 0, and in this integral this ln x was excluded, And while I was evaluating this residue, this was fairly easy to see that I can find the residues about e ki power iota pi, e ki power iota 5 pi by 3, and e ki power iota 5 by 3. And overall, I concluded the answer 2 pi upon 3 root 3, the same answer which I've done using a special quantum. So this sums up our class. In the next class, we are going to do a question on zest. And then very next class, we are going to see how to exploit periodicity in order to find the quantum integration, and which will sum up the phase 1 of our complex analysis. Okay.